Good day and welcome back for part 3 of our discussion on maximum and minimum values. In previous videos, we introduced the idea or concepts related to what it means for something to be a maximum or minimum, as well as the associated values. And we finished up our previous discussion on the extreme value theorem, and I want to pick up and highlight it to start today's discussion. The extreme value theorem tells us that if we have a continuous function on a closed interval, then that function will attain an absolute maximum and an absolute minimum for some inputs in that closed interval from a to b. So graphically, if I was to randomly sketch some continuous function going from a to b, maybe something along these lines, intuitively in the graph we can very clearly see where these maximum and minimum values occur. For example, the absolute maximum occurs at the right-hand endpoint of the interval, and we can see the absolute minimum, which occurs somewhere inside that interval. And this is exactly what we should expect to happen in general. Absolute maximums and minimums occur at exactly two types of points. They will occur at an endpoint of the interval, as the absolute maximum did above, or at a point inside a to b with a horizontal tangent line, which is exactly where we left off in our previous video. That absolute maximum and minimums occur at an endpoint of the interval or a point in between where that tangent line is horizontal. And remember, at this point, let's call it C, corresponding to a horizontal tangent line, the derivative is determined by f prime, which will be equal to 0. And it turns out that these points C that make the derivative equal to 0 are going to play a special role in upcoming topics, and they're worth investigating a bit further. So to further investigate these points, I want to state a property. If f has a local maximum or minimum at x equals c, and the function is differentiable there, then f prime of c, as we've seen in our previous examples, will be 0. And note, the picture is really kind of telling us what's happening. If we consider something similar to what we saw on the previous page, at this local maximum, which occurs at, say, C, where the function is clearly differentiable in the sense of the graph being continuous and not having any sharp points or cusps, the tangent line is horizontal. So that's telling us that f prime of C is equal to 0. So if there is a local maximum or minimum at C and f prime is defined, then f prime of C will be 0. And of course that leads to a natural question. Can we reverse this statement around? That is to say, if f prime of c equals 0, does that imply f has to have an absolute maximum or minimum at c? So maybe pause the video and think about that question for a moment. And it turns out the answer is, surprisingly, no. And kind of a key example to illustrate this would be the common curve given by the graph of the function x cubed. Roughly speaking, the graph of x cubed looks something like this. And if we were to just do a couple quick computations, if we differentiate x cubed with the power rule, we would get back 3x squared. And I would just like to note, if you wanted to solve where this is equal to 0, so the question mark indicates I want to solve for that x value, the only solution is x equals 0. So f prime of 0 is 0. But if we look at the graph, at 0, we do not have a local maximum or minimum, but the tangent line actually is horizontal there, whether my picture illustrates it or not. So x cubed provides us of an example where the derivative is equal to 0 at 0, and x equals 0 is not a local max or min. So even though the reverse statement of this property is not true, which I wanted to state just to make sure we're all cautious of that fact, when we do have local maximums and minimums, which are things we want to be able to locate, they do occur typically where the derivative is equal to 0. And because of that, we're going to give these values a special name. We will say that a critical number, and I will almost always actually refer to these as being a critical point, and for shorthand I'll say CP, of a function f, is this number c, so we think of it as an input. It has to be in the domain of the function f, such that one of two things happens. F prime of c equals 0, or f prime of c is undefined. So just to reiterate, in order to be a critical point, you have to be a value in the domain of the function that makes the first derivative 0 or undefined. So a typical question we can now ask you is, for some given function, can we find all of the critical points? So let's see if we can do that. In order to find the critical points, they need to be in the domain of the function. So I'm just going to simply start by noting the domain to make sure that I don't miss maybe one of these more what I consider subtle types of critical points. So f is a polynomial, which means it's defined everywhere. So its domain is the entire real line. So we are looking for any real number now that makes the derivative 0 or the derivative undefined. So differentiating this term by term using the product rule, we'd have 1/3 times 3 x squared minus 2x plus 1. And what we would like to know is, what are the values of x that will make this function equal to 0? This factors nicely, and there's only a single value, x equals 1. So in terms of the critical points of this function, the only critical point occurs at x equals 1. That is the value that makes the first derivative equal to 0. And likewise, the first derivative is defined everywhere, so we do not have to worry about this more subtle type of critical point. With one example under our belt, let's move on to the second example. We're given another function. I will get us started. Let's just think about the domain of this function. The domain would occur whenever that quantity underneath the square root is not negative, which means whenever 1 is bigger than or equal to x squared. And that occurs precisely when x is between -1 and 1. If x is larger than 1 or smaller than -1, that inequality would most certainly not be true. So a critical point of this function is going to be a value in this closed interval from -1 to 1, where the first derivative is 0 or the first derivative is undefined. And I would like you to pause the video, find the derivative, determine the critical points. And hopefully at this point you have done so. If not, pause the video and think about the problem for a few minutes. So let's go ahead and differentiate the function. This is something that requires the chain rule. We have an inside function 1 minus x squared, and the outside function is a square root. So we take the derivative of the outside function, we evaluate it at the inside function, and we multiply it by the derivative of the inside function. So note in this case, the 2 in the top and the 2 in the bottom cancel, and we're left with minus x over the square root of 1 minus x squared. And to find the critical points, we take this expression, we set it equal to 0, and we solve for x. A fraction is equal to 0 precisely when the top is 0. So we end up with a critical point corresponding to x equals 0. But remember, there are these more subtle types of critical points that can occur, and that would be something in the domain of the function where the first derivative is undefined. So I really do need to take a moment and think about the domain of f prime. So the domain of f prime, well, once again, we have to worry about that square root, so we need the 1 minus x squared to not be negative, but we're dividing by it. So 1 minus x squared has to actually be positive, which means 1 needs to be bigger than x squared, which gives us the interval from minus 1 to 1. And note in this case, we can make the observation f prime of x is undefined when x is equal to plus or minus 1. So this is the more subtle type of critical point. Plus or minus 1 are in the domain of the function, but the derivative is undefined at plus or minus 1 because they cause you to divide by 0. So when you're dealing with fractions like we are in this case, that's when you really have to be careful of this second or more subtle type of critical point. So critical points occur at 0 and plus or minus 1. So that finishes up our current discussion. In our next video, we're going to link this back to the extreme value theorem and discuss the procedure we will use to find absolute maximums and minimums of continuous functions on closed intervals. So stay tuned and take care.